12s. This is a short little section on integrating the exponential function that hopefully will go quite quickly. Now, in order to integrate the exponential function, we again have to first go and look at the derivative of the exponential function so that we can then go and reverse the process, which we always do with integrals. So if I find the derivative of e to the power of x, my answer is e to the power of x, because this is one of the properties of e to the power of x, is that the derivative is e to the power of x. So therefore, I can then make the statement that the integral of e to the power of x dx is then also just equal to e to the power of x plus c. So quite nice, easy, simple, straightforward. Right, how can they complicate it? Not really by much. Pretty much it's back to that whole idea of the reverse chain rule, meaning if I now go and I have a compound function, so a function inside of a function. So let's first quickly look at when we found the derivatives of these compound functions. So if I had fx is equal to e to the power of x, and we had gx is equal to 2x, and I wanted to find f of gx, so I wanted to put the function 2x inside of function e to the power of x, then this would have been e to the power of 2x. Hopefully you guys can spot that quite easily. Pretty much all that happens is right over there where x used to be, I now put gx. So where x used to be, I now put 2x. So that's my compound function. Now, you'll recall that the moment we find the derivative of a compound function, we have to go and we have to use the chain rule. So according to the chain rule, we find the derivative of the outside function first, keeping the inside function exactly the same. So we don't touch it. And then only do we go and we find the derivative of the inside function and we multiply that by that derivative of the inside function. So that would mean, as we were doing when we were finding the derivatives of this exponential function, we would then go and say that the derivative of that e to the power of 2x is then equal to e to the power of 2x, because the derivative of e to the power of anything stays exactly the same. But I then have to go and find derivative of the inside function, which in this case the derivative of 2x is then equal to 2, so I just have to multiply by that 2. So hopefully this is just to jog your memory on how to find the derivative of that exponential function. But that then means, coming back to what we do with integration, we can then say the integral of e to the power of 2x is exactly the same principle as we were doing with the trigonometric integration using that reverse chain rule, saying I need that 2 right over there. So I need to create that 2, but if I multiply by 2 over here, which by the way, if you think about it, that is the derivative of the inside function. So that's just using the reverse chain rule. But if I put that 2 there, I have to put the half there, which then means the derivative of that inside function, that's what always disappears. I only have to integrate that e, which is my outside function, and the integral or the derivative of e stays e. So this is then just going to be a half times e to the power of 2x plus c, which then means it's e to the power of 2x over 2 plus c. But I can use that shortcut that I showed you guys with trigonometric integration, where if I have an inside function for e, I then, oh, and very important, I did state this, if I have an inside function for e and the derivative of that inside function is a constant, in this case 2, you can actually just skip ahead and you can go straight from there to there, saying the derivative of e to the power of 2x is e to the power of x, but because the derivative of the inside function is 2, constant, I can then just divide by 2. So you can actually use that shortcut here as well that I showed you to use in trigonometric integration. Right, so let's do some examples. You'll see the examples are very straightforward. So with this one, we start by saying the integral of e stays e. So it's e to the power of 3x minus 2. But then, because there is an inside function over there in that exponent, I just have to ask myself, what is the derivative of that inside function? And hopefully you guys should spot it's just 3, which means that is a constant value for my derivative. So I can use that shortcut, I can divide by 3, and then I can go plus c. You could have done it the long way again. You could have put the 3 over there, you could have put the third over there, and then use the reverse chain rule. But I think this is pretty self-explanatory after the trigonometric integration. Right, now this one. For this one, we have to manipulate it slightly. We can put the 4 on the outside because that's a constant multiple. And then I can change that e to the power of 3x to e to the power of minus 3x dx. Okay, so I can bring the 4 down, and I can say multiply by the integral of e stays e, so that's going to be e to the power of minus 3x. But I have to go to the inside function, and the inside function's derivative is a constant, which is negative 3. So using that little shortcut, which is pretty much still the reverse chain rule, much faster, we're going to divide by negative 3. And then I can clean up my coefficients. Oh, by the way, cleaning up my coefficients, it's something that they do want you to do. They don't want you to do lots of simplification. But if you have like a quick multiplication like that, please just clean it up. So we're going to say it's minus 4 over 3 e to the power of 3x plus c. By the way, I just went and I moved it into the denominator so I could change the negative exponent to positive. If you'd actually left that e to the power of negative 3x in the numerator, they will not penalize you for that. So they don't penalize you for negative exponents, but they could potentially penalize you if you don't clean up the coefficients. So just watch what you're doing. Right, next example. So this one requires a little bit of algebraic manipulation. So hopefully you guys will recall from core mathematics that if I can simplify the algebra, I need to simplify the algebra. So in this case, I'm going to say it's the first term divided by the denominator plus the second term divided by the denominator, which is my distributive law for fractions. So I can just go and say it's the integral of e to the power of 3x divided by e to the power of 2x, which is e to the power of x, plus 4 divided by e to the power of 2x, which is going to be 4 times e to the power of negative 2x dx. So if you can go and simplify the algebra, please do so, especially if the sum now becomes incredibly easy to do. So now I can find the integral of the first one plus the integral of the second one. We did discuss this concept as well. If there are pluses and minuses, I just find the integral of each one separately. So the integral of e to the power of x is just e to the power of x. Plus, now over there, I'm going to bring the 4 down as a constant, and I can quickly just write the integral if you want me to. That's absolutely fine. Let's write it. It's not really necessary, but I can write the integral of e to the power of negative 2x dx, and over here I already put the plus c. The reason I put plus c over there is I've already found the integral of that one, so the moment I find an integral I need to put plus c. I'm not going to have to put plus c again when I find the integral of that one, by the way. So bring down e to the power of x, bring down the 4, and then over there this is going to be e to the power of negative 2x, because remember the integral of e to the power of anything stays the same. However, careful, because there's an inside function there, negative 2x, and the derivative of negative 2x is negative 2. So I have to divide by that negative 2, and I can bring that plus c down. So I'm going to clean up over here, and I'm going to say it's e to the power of x minus, and then obviously 2 goes into 4 twice, so it's 2e to the power of negative 2x plus c. And like I said, if you do leave that negative exponent, they don't actually penalize you. They're absolutely fine with negative exponents. Now this one is exercise 4.1 on page 86, number 8. Just again, to show you that a trigonometric, apologies, brains full of trigonometry. This one specifically, again, there's algebra involved. So just like with the previous video, I'm not going to do this one. I want you to do it. I will, however, in the notes on the video, I will complete this so you can go and check on the notes on the video whether you've done this correctly. So please go and practice, because like I keep on telling you guys, it looks fine when I'm doing it, but you need to go and sit down and you need to go and practice and you need to go and see if you can get these things right. Thank you for listening.